A Few Digital Basics by Ralph Eagle, Director, Department of Pathology at the Wills Eye Hospital and the Sidney Kimmel Medical College at Thomas Jefferson University in Philadelphia, Pennsylvania. Resolution. Digital images are composed of small colored squares called pixels. Resolution usually is defined as the number of pixels per inch. In the past, this was often called DPI, or dots per inch. Lower resolution images have larger pixels, and higher resolution images have smaller pixels. When you're using Adobe Photoshop to modify your images, I think it's wise to use pixels as a unit of measurement in your rulers. This avoids the need for conversion and potential confusion. Remember, for publication, the resolution should be at least 300 dpi. A 6x4 inch photo at 300 dpi is 1800 by 1200 pixels. A smaller 3x2 inch photo is 900 by 600 pixels. The resolution of projected digital presentations is limited by the resolution of the digital projector. The resolution of a series of digital projectors is shown below. Currently, many projectors are XGA with a resolution of 1024 by 768 pixels. If you have images that are larger, you're just wasting memory. However, I must admit that I tend to use 2048 by 1536 images because they can be extracted and used to make 6x4 inch figures for publication. This is a very low resolution image of an eye with retinoblastoma and leukocoria. This was considered a high-resolution image in the past, 2048 by 3072, 18.4 megabyte image. Let's look under higher magnification. In this area, we can see the size of the pixels. The resolution of digital images keeps getting better and better. I took this photo of some Indian physicians with a Nikon D850 digital single lens reflex camera. The resolution is 8256 by 5504 pixels. Let's look at this young lady's eye. The pixels in this high-resolution image are so small that you can barely make them out. Here's another photo I took with my Nikon D850 digital camera. It shows the famous photographer and retinal specialist Howard Schatz. As we increase the magnification, we can see how small the pixels are in this high-resolution image. Higher resolution image files are very large. They tend to use a lot of memory. Fortunately, memory has also increased markedly in recent years. In this table, we see that the Nikon D850 image at the bottom actually occupies more than 45 megabytes of memory. Here again is that very low resolution image of a retinoblastoma with leukocoria. In the olden days of telephone modems, it would actually take 3 seconds to download this terrible image. Here's what was considered a high-resolution image at that time. It would actually take 10.6 minutes to download this image with a telephone modem. I bought my first Macintosh, a Macintosh Plus, in 1986. It had 1 megabyte of RAM. The capacity of my first external hard drive was 25 megabytes. That would hold approximately 1/2 of a current high-resolution photo. Remember, you can decrease the resolution of a high-resolution image, but you can't increase the resolution of a low-resolution image. The computer program just manufactures data. Okay, let's talk about color. There's different types of color. There's RGB color and CMYK. These are the ones we're going to talk about. There's also HSB, stands for hue, saturation, and brightness, and there's something called lab color as well. RGB color. This is the type of color that's used in computer screens and smartphones and video projectors and televisions. RGB stands for red, green, and blue. These are the light primary colors. We combine the red primary color with the blue primary color and the green primary color. Light primary colors are additive. Red and blue equals magenta. Red and green equals yellow. And blue and green equals cyan. Red, blue, and green equals white. Computer screens and TV tubes have red, blue, and green electron guns, or more commonly today, red, blue, and green phosphors. The red, green, and blue phosphors correspond to the red, blue, and green cones of the retina. Each color channel on the computer has 256 levels of intensity or brightness between black, which is 0, and the pure hue, which is 255. Now here's the red channel, black 0, bright red 255. The electron gun is sort of like a flashlight that has 256 clicks or levels. Remember, in additive color, red, blue, and green equals white, and all three color channels set at 255 equals white. Here's the screen of an old laptop computer. The left half of the screen is white and the right half is black. I put the screen of the laptop on a flatbed scanner and scanned it. The scan disclosed the vertical bars of the Sony Trinitron screen. Maximally illuminated bars of red, blue, and green are seen on the white part of the screen. The white part of this computer screen is composed of 3 vertical bars of red, blue, and green, but only the red columns are noted in the red star. This is the color picker in Adobe Photoshop. We're looking at the white color, and we can see that it's composed of 255 red, 255 green, and 255 blue. In contrast, black is composed of red 0, green 0, and blue 0. This is the color swatch panel of an older version of Adobe Photoshop. The computer screen is examined under higher magnification using a dissecting microscope. In the red swatch, only the red column is illuminated. Remember, in additive color, red and green equals yellow. In the yellow swatch at right, the red and green columns are illuminated, but the blue column is dark. This is what one would see in the Sony Trinitron screen. Red and green equals yellow. In a green area of the screen, red is 0, green is 255, and blue is 0. And in the Sony Trinitron screen, all 3 columns in the white area, just the red column in the red area, just the green column in the green area, and red and green in the yellow area. The vertical columns of the Sony Trinitron screen are no longer used. This is an Apple iPhone XS Max with a Super Retina display. We'll examine the screen with the dissecting microscope and concentrate on the Chrome logo. As the magnification increases, the pixels in the Super Retinal display begin to become visible. The red dots are seen in the red area at top, red, green, and blue in the white area in the middle, and blue dots predominate in the blue area at the bottom. Red and yellow are seen in this part of the display. As we said before, red is 255 red, 0 blue, and 0 green. Blue, 255 blue, green, 255 green. White, 255, 255, 255. Yellow, 255 red, 255 green, 0 blue. Magenta is red and blue, 255 red, 255 blue. Cyan, 255 blue, 255 green. This red-orange color is composed of 227 red, 17 blue, and 40 green. Here's a pink color. It's a 255 red, 150 blue, 100 green. This sort of horrible blue color is 100 red, 100 green, and 255 blue. This sort of mustard color, 247 red, 48 blue, 155 green. Now here's a photo I took of some flowers a few years ago. It's in Photoshop. Photoshop has an eyedropper color sampler tool. Using the eyedropper, I'm able to sample the color in the red flower. When I sample the color with the eyedropper, a color picker window appears. In the color picker window, we can see that the color is made up of 241 red, 91 green, and 92 blue. Let's look at this purple flower. We see the eyedropper sampler tool. The color picker appears. The color picker shows that the purple color we sampled is composed of 186 red, 114 green, and 118 blue. Okay, you talk about computers generating millions and millions of colors. Well, how do you get millions and millions of color? Well, 256 times 256 times 256 equals 16,777,216 colors you can generate using different combinations of the 3 color channels. The primary colors used in painting are different. They are red, blue, and yellow, and the secondary colors are purple, orange, and green. Mixing of pigments results in the absorption of light. This is called subtractive color. CMYK is the type of color used in 4-color printing that uses colored inks. CMYK stands for the 4 colors of ink: cyan, magenta, yellow, and black. This is a form of subtractive color. When inks are used, you get a smaller number or gamut of colors: cyan, magenta, yellow, and black. K stands for black. When printing was done with plates, the black plate was called the key plate because it contained the artistic detail or the key information. When we combine inks, it's subtractive color. Let's look at some examples of CMYK. This is a very poor resolution color printing from a Sunday supplement. Under higher magnification, we can see the different dots of color. CMYK, again, C and Y's. Cyan and yellow equals green. The paper appears white where no ink is present, and black areas are composed of all 4 of the inks. Here's an example of high quality of 4-color printing from the National Geographic. Probably can guess what this photo is going to be. The Afghan girl. Under higher magnification, we see the smaller dots of cyan, magenta, yellow, and black ink. When the first Macintosh computers came out in the early 80s, people were blown away by the graphics. The early images were called bitmap images, shown here in this example. Bitmap images were composed entirely of black and white pixels. Grayscale was a subsequent advance in computer imaging. Grayscale images are composed of pixels with 256 levels of gray between white and black. Again, the computer can generate 256 levels of gray between black and pure white. Black is 0, of course, pure white is 255. Here's an example, a 0, an 85, a 120, and a 255 gray. Here again, 255, 255, 255 equals white. 200, 200, 200 is this light gray, 150, 150, 150, darker gray, 100, 100, 100, even darker gray. So all 3 of the color channels are outputting at the same number to give you a gray. Let's talk about fonts. There are 2 categories of fonts: serif fonts and sans serif fonts. Times is a classic serif font. In typography, a serif is a small line or stroke regularly attached to the end of a larger stroke in a letter. Sans serif fonts are block letters that lack these small lines or strokes. Sans is a French word that means without. Arial and Helvetica are classic sans serif fonts. Sans serif fonts are recommended for digital presentations because they're easier to read. Serif fonts are not recommended because they're harder to read, especially when they're small, and especially when you're dealing with a low-resolution projector that can pixelate them.
Bold sans serif fonts are recommended for digital presentations because they're easier to read, particularly when they're small. Again, small serif Western fonts like Times are harder to read than sans serif fonts like Arial, especially when they're small. Bold sans serif fonts like Arial are recommended because they're easier to read. I generally use Arial Bold, and I never use standard templates for my presentations. If you're not using your own computer to present, you're giving a presentation somewhere, I think it's wise to use standard fonts like Arial. Unusual fonts like Braggadocio shown here may not be installed on the host computer, and this can lead to font substitutions that can affect the spacing and layout of your slides. Another rule, never place red letters on a green background or green letters on a red background. In the eye, shorter wavelengths of light like green are focused in front of the longer red wavelengths. Whether red or green letters appear sharper depends on an individual's refractive error and adequacy of correction. Ophthalmologists and optometrists often use a duochrome test based on this principle when prescribing glasses. You don't want to do a duochrome test on your audience. I personally think that a rainbow of colored letters on a black background doesn't look very good. Do these blue letters look blurry? You're not going blind. Your eye is actually about 1 diopter myopic or nearsighted for blue. The focal point of the shorter blue wavelengths of light is in front of the retina. I'm going to do something. I'm just going to change the color of the font here. You can see how it sharpens up. Didn't do anything else, just change the color of the font. And again, the red is sharp and the blue isn't. Okay, less is more. This is a very busy word slide. It contains accurate and important information, but the amount of the information and the size of the graphics are too small to allow the audience to easily assess and comprehend it. When you give a presentation, go for clarity. Keep it clean and simple. Your word slide should be readable and your images should be visible. I like big pictures. Now here's a PowerPoint slide from somebody's presentation from years ago, again, bone marrow 2004. Again, this photo has lots and lots of wasted space. I'd rather look at the big picture. You can see more in a big picture. Another example, 2 examples of a corneal dystrophy. Lots of wasted space. I'd like to see the details. I want to see the big picture. Here's another example, a word slide with more than 25% of wasted space. In this instance, the presenter had digitized a prior slide presentation. The title at the top of the slide was helpful in sorting slides on a light box. This is unnecessary in a digital presentation. I reformatted the slide and removed the empty space. The pictures are bigger and easier to see. The images in this slide were inserted into a standard template. Again, the size of your image is not limited by the image size in the PowerPoint template. You can stretch the image and fill the screen. Too much animation can distract and detract from your message. And let's do that again. Too much animation can distract and detract from your message. I think animation should be used sparingly. Sometimes put a little bit in to wake people up every once in a while, but I think it can really detract from a presentation if it's overdone. Custom backgrounds. I make custom backgrounds all the time. This is a custom background in the back of this slide. Using Adobe Photoshop, it is very easy to make custom backgrounds that are specific for your talk. Here's a photo of Oedipus and the Sphinx that I found on the internet. I recently had to give a lecture on Oedipism or autoenucleation, and I used this image to make a custom background. Here's the title slide for my talk. A few years ago, I had to give some lectures in Japan. As we were nearing the airport, I took this photo of Mount Fuji and was able to use it as a custom background for the title slide for one of my lectures. I also made a custom background of a Japanese red maple, and I transitioned it back into the original color photo at the conclusion of my lecture. It's very easy to make custom backgrounds with Adobe Photoshop. This is a color photo of Venice Beach in California. In the first step, we want to get rid of the color and convert the image to grayscale. We use the image mode command to convert to grayscale and discard the color. Here's the grayscale image. Then we use the image mode command to convert the grayscale image back to RGB. Next, we open the image adjustment menu and select hue saturation. In the Hue Saturation panel, we select Colorize, using the checkbox. We then use the sliders to select Hue, Lightness, and Saturation. I personally prefer dark blue backgrounds. Transitions. I tend to avoid elaborate and showy transitions because I believe that they can detract from your presentation if used excessively. I tend to use transitions to emphasize points. This is a photomicrograph of a heavily pigmented tumor of the optic nerve called a melanocytoma. These tumors are so heavily pigmented that pathologists need to bleach the sections in order to adequately assess them. Here we see the transition from the normal to the bleached section. Here's another example. This is a macro photo of a carcinoma of the retinal pigment epithelium, a very rare eye tumor. Here we transition from the gross photo into the histopathology and demonstrate the location of the tumor on the inner surface of Bruch's membrane. This is a clinical photo of a rare tumor of the iris called a tapioca melanoma. This is a high magnification macro photo showing nodules of tumor on the surface of the iris. We examine the specimen using scanning electron microscopy. This is the black and white scanning electron micrograph. I used Adobe Photoshop to colorize and highlight the tumor cells. This makes for a rather striking transition. Here's another transition between the normal and false colorized micrograph under higher magnification. Keynote versus PowerPoint. I prefer Keynote. Keynote is an Apple program. I think that Keynote is a better program, but it can only be used on a Mac. I think it's easier to use. You can open PowerPoint presentations with Keynote, and you can export Keynote presentations to PowerPoint. When I need to distribute a presentation as a PowerPoint, I generally will make it in Keynote and then export it. Again, you can export Keynote presentations to PowerPoint, but you have to be a little bit careful. Animations may not work or may not be as good. For example, a dissolve in PowerPoint tends to be pixelated compared to the smooth dissolve in Keynote. You can have problems with drop shadows, and font layout may change. Remember, you are the show. If you're giving a presentation, don't read your slides by staring at your computer on the podium. Reading your slides is a kiss of death if you want to get your audience totally disinterested in your presentation. Finally, remember, a PowerPoint or Keynote presentation is never done. Thank you.